The next presentation is by Nils Anderson, and Nils has shown up on the screen. Nils works for Alberta Environment and Parks. He's based out of Grand Prairie. He's working with the science team doing modeling work on horn growth and management alternatives to demographic modeling. And he'll tell us about some of that work today. Nils.
Okay, I'll just share my screen here. Okay, so I've kind of condensed my title a little bit. I'm going to talk to you guys today about the size at age relationship in Alberta's bighorn sheep. So as Mark mentioned, this is kind of spurred by the structured decision-making process that we're using to engage with sheep hunters regarding bighorn sheep management in Alberta. And kind of where it fits in is the need to develop a bit of a simulation model that can assess alternative management strategies. And largely that's kind of to answer those what if questions that stakeholders always bring up to us. And to try to illustrate the trade-offs between different options that are out there. One of the big challenges that we run into with bighorn sheep, at least in Alberta and in a number of other jurisdictions, is that most population models work based off tracking the age of individuals through time, but our management regime and our survey monitoring approaches work based off of size. So we can work with that as long as we understand the relationship between age and size. And we can use our hunter harvested sample to help inform that. So we can do it based off of a very data-driven approach. So within this presentation, I'm going to try to just speak to how we can convert from age to size and size to age. Each has a bit of a different application for us. So first off, I'll just a quick reminder that I'll be talking about the size classes that we use in Alberta in the management context. So those are the ones across the top. They do generally align with ones that you may be familiar with from Geist, but one notable difference is that we split the class 3 rams into 4/5 curls and 3/4 curls. And that's just to reflect our current regulation, or one of the more common ones in Alberta anyway, that rams become legal at 4/5 curl. Now, the way these are based is more or less using morphological landmarks to assess how far around a circle those horns have grown. So although they're very strongly dependent on age and length, they're also affected by how tightly that horn curls. So we've tried to develop an approach that describes how that horn grows in 2 dimensions to hopefully explain away some of the noise that's in the data there. And you know, when I first thought of this, I thought it was pretty original, and then a colleague passed along Bill Wishart's master's thesis, and turns out he was already onto this 60 years ago. And you know, just included a few figures here. One thing of note, in addition to this nice graphical illustration, Bill also summarized this based on the percent of each age class that has achieved a given size. Now, 60 years later, the concept is really the same, but we can use the annuli measurements that we've been taking at our registrations to tell us how big a given sheep was in each year of his life. That helps us make the most of each of those 150 rams that we harvest in Alberta each year. So when we're looking at going from age to size, as I kind of spoke to in the example from Wishart's thesis, basically the question that we're answering is, if a ram has reached a given age, how big might he be? And I've framed that question kind of intentionally because of the way we end up applying it in the model. So the answer to this question really isn't affected by non-hunting mortality, because we're assuming that is not size dependent within an age class. So it varies depending on how old a sheep is, but not how big it is. necessarily. And this is what we use to determine the proportion of each age class that would be available for harvest within the model. Once we know that, then we can remove them from the model. So here's a look at some of the raw data. This is using 193 rams registered in the last couple of years in Alberta, and gives you a bit of an idea of the variability in how sheep grow to grow through these size classes. One thing I'll draw your attention to is you'll notice the way the data kind of thins out near the top here, especially in the older age classes. And that reflects a survivor bias. So kind of along the lines of what Marco was describing, we're running into it again here, that these very fast growing sheep tend to be exposed to harvest a little earlier in their life and don't have the same probability of continuing to exist as a living, breathing member of the population. So survivor bias is a very common feature of size restricted harvest. And at least for our applications here, it's not necessarily a problem because it actually does represent those sheep that have survived to be standing on the side of the mountain. But we do need to address it when we start exploring different alternative size restrictions or alternative harvest rates, because those two things will affect the nature of that bias. And in order to do that, basically the approach we've taken is to first erase that bias and then reintroduce the bias that we would expect for that given scenario. So basically the way we do that is we project each individual sheep past its death based on kind of the consistent pattern of declining growth increment with age. So I've kind of included those data points to represent the ghost sheep in there. And in general terms, this lets us fill in that gap left by the survivor bias. And in theory, at least, this would represent the age size relationship in the absence of any kind of size selective harvest. So it's a good starting place for us. One thing to notice here is within the sample that I'm showing you here, so far we don't have any sheep or haven't gotten any included in here that are over 12 years old. But for the purposes of at least this talk, I'll just assume that those ones would have achieved full curl, at least most of them. So now let's talk about reintroducing a survivor bias that we would expect to see in the real world. So I'm gonna talk to you a little bit about kind of my neck of the woods here, north of the Athabasca River. Over the last decade, we have observed a 32% harvest rate of our legal rams. So 32% of those rams that are 4/5 curl that start the hunting season end up harvested by the end of it. So the way we reintroduce that survivor bias, it's going to affect any ram that's over, or any sheep year or data point that's over the 4/5 mark. And basically we just weight those points by the cumulative exposure to harvest. And I could go into the details of the gruesome details of the math and converting that nice figure into this kind of ugly table, but maybe I'll save that for if anybody wants to follow up after the fact. So in terms of how we apply this to a population model, the main take home out of that is the proportion of each age class that is large enough to be available for our legal harvest. And this is only based on the last 10 years out of everything north of the Athabasca River. But what we'd expect to see is that about 10% of our 4-year-olds would be legally available for harvest, 29% of 5-year-olds, 66% of 6-year-olds, and so on. Now, the way we end up applying that in the model is we have that 32% harvest rate, and each of these figures essentially becomes the availability for harvest. So you multiply the two together and then apply that to the age class total to determine how many sheep of that age class were removed by harvest. Now, the way I kind of think of it is our handling of survivor bias and the data set here, it does represent some improvements over previous work, mainly in terms of just making it very explicit what this relationship is trying to represent. as well as making it very flexible to explore some alternatives. We can go a lot of directions with this. Now, the other application that I mentioned is going from size to age, and this isn't as commonly used in the population simulation context. But the one place we use it is to convert our size-structured survey results to an age-structured initial population to start the model from. And it just answers the question of how old are the sheep in a given size class. Now, in this case, we do need to correct for non-hunting mortality. And the way I can kind of explain that is that, there's multiple ages within our 3/4 curl sheep, for example. And the older classes are going to be a little less abundant than the younger classes, just because they've had to survive more years of non-hunting mortality. So some of them will die out a little bit as they get older. Just a quick plug for the Wild Sheep Foundation of Alberta, who provided a lot of the funding for our surveys that are very important in kind of all these exercises. So in this case, we still have to deal with that survivor bias, as I mentioned. We can work with that previous table and just basically invert the rows and columns, and then include the non-hunting survival, again, cumulatively, for the rams in each age class. Again, a very ugly table. And in this case, it's actually relevant to females as well. And not because we actually classify females based on size, but just all those ewes that we count on survey, we still want to distribute them across the age classes in a reasonable way. I'd also point out that here we've realized a 0.6% harvest rate on lambs and adult ewes in this area. We do have special license opportunity, limited entry hunting opportunity for those sheep in Alberta. So in terms of next steps here, what I've shown you is kind of a preliminary look at where we've managed to develop this method to date. Some of the aspects that we haven't yet fully addressed are how sheep broom off the ends of their horns. So currently we're basically modeling the sheep as if they didn't break off the tips of their horns as they grow. I'm hoping that after we get our 2020 data in, we'll be able to look at some regional specific relationships, sort of to describe how sheep are growing in the southern parts of the province, the central parts of the province, and the northern. Another aspect is, as I mentioned, I think a two-dimensional model of how horns are growing is a big improvement over looking just at length. But horns do grow in 3 dimensions, and whether a sheep is legal or not will also be affected by how far out to the side the horn tips spread. So we're collecting a little bit of additional data this year to assess how much of a difference a 3-dimensional model of horn growth would make, and whether those additional measurements are worth it for our purposes. I'm also hoping with the 2020 data to use some subsampling or bootstrapping techniques to estimate confidence intervals around those availability for harvest figures that I showed you earlier. And even with these limitations, we have started to dip our toes into some alternative scenarios, at least in a preliminary manner. And that's stuff that we're starting to engage back with stakeholders on to kind of spur that conversation and get a bit of feedback in terms of what are the outputs, how do we talk about a simulation model output in a way that's relevant to those stakeholders that they can kind of grab onto and engage with. So with that, just like to thank everybody who's contributed on this, especially the members of our science advisory team for our engagement process. They've provided a lot of great comments and conversation on this approach. Like I mentioned, Wild Sheep Foundation of Alberta, as well as the Sheep Hunters of Alberta, who brought in heads for us to look at. And all the environment and parks wildlife biologists who flew the surveys, registered the sheep, and also provided a lot of feedback and guidance and advice on this over the last few years. So with that, if there's any questions, I'd be happy to answer them.
Yeah, I think we're running over quite a bit, so we're going to have to move along. But there are, you do have the Q&A alternative for answering questions in writing. So